So I have opened here my spreadsheet in Excel. I'm going to, to view it in such a way. So I'm going to freeze the panel. I like to keep this first column and those other two lines visible all the time. Okay, it's a very convenient way of using Excel. And I'm going to come up with a table like a mass, length, period, and gravity. Okay, just like this one that we have in the handout. Here you go. You go ahead, write down the mass. You always put the kilogram there at the first line. Do not put the kilograms in the cells like it's indicating in the handout. Put the length in meter. Yeah, here you go. Period and gravity. Period. Always put the units there, and G, meters per second square. Okay, the square here of the second, you have to highlight it, right click and format the cell. This window is going to show up. You check the superscript box, and now you have your G as in meters per second square. That's my table I'm going to do. I like always to boldface this header of the table and put a 6 square there in the header of the table. How many data points are we going to collect? We're going to collect 1, 2, 3, 4 data points. Okay, so let's create our table with 4, 1, 2, 3, 4. Here you go. Make this table look nice. And next, it's going to be 1 kilogram. You're now going to change the mass of the pendulum. And then, adjust the length of the pendulum. Let's do, everybody do the same length. Okay? And let's take a look at the simulation. We can get anywhere between 1 meter and a half. Oh, no, sorry, so that's the mass. We can get anywhere between 60 centimeters, 1 meter and 10 centimeters, right? Like I mentioned before. So let's do the following. Let's get a maximum length of 1 meter, and then we do 75 centimeters. We do half meter. Let's see, 1 meter, 75, half meter, and 25 centimeters. Let's do those values, right? Let's start with 1 meter here. 1 meter, 75 centimeters, half meter, and 0.25 centimeters. You're going to determine the period of the pendulum. The acceleration of gravity is going to be 9.8 meters per second square, which is the acceleration of gravity of the Earth. And that's the data that you're going to collect, the period. Going back to the simulation, all I have to do is to start my period. Oh, wait a minute. Yeah, not yet. Don't start it yet. First, you have to start your timer because the simulation is paused. The timer doesn't move at all, and it's going to be in slow. Okay. Let's count one single period of oscillation. So the moment I play my simulation, the timer is going to start as well. Here you go. Watch it and wait until a full period is completed. The moment I pause the simulation, the timer is going to pause as well. Wait until it reaches this point here, right here. Okay? So it takes 2.04 seconds for this 1 meter long period. 1 meter long pendulum to complete a full period. 2.04 seconds. Now we're going to change the length to 0.75 meters. And repeat the simulation. You know, zero, you gotta reset your timer. You start the timer, and the moment I start the simulation, you should be able to time a full period. Pause when it reach a full period. Here you go, it's coming, stop. 1.74. 1.74. Half meter, let's go for half meter. No? Reset your timer. You start the timer and you start the simulation. Here you go. That's half meter now. Wait until it returns to initial position and we stop. That's 1.46 seconds. 1.46 seconds. This simulation that we're doing is a very realistic one, okay? You can do this experiment in the lab, and that's exactly how it is done. What's not done in the lab is that you cannot slow down the oscillation of the pendulum, of the real pendulum. And you gotta be very careful when you stop your timer, right? In this case here, when I pause the simulation, the timer also stops. So those are the only two details that does not show up in real life. Zero my timer, start the timer. Oh, wait a minute. We gotta decrease the length to 0.25 meters. Here you go. And start the simulation. Here you go. Wait until full period. Right in here. I'm getting 102 seconds. 1.02 seconds. That's my first graph. Let's go back to the simulation here. Again, I choose length 1 meter, 75 centimeters, half meter, and 25 centimeters. What else do you have here? Here you go. Complete the table below. Repeat the investigation, but for each trial, item number 4. I use only the mass of the pendulum, leaving all other variables constant. Same length, period, and gravity every time. Okay, repeat the investigation, but for each trial, just only the mass of the pendulum. Okay, so let's go back to the simulation now. We're going to come up with a different. Here you go. It's actually the same table, right? It's just a different way that you're going to collect the information. So here you go. I'm going to repeat this table right in here, and I'm going to choose a single length. We're going to find out what the period is. The acceleration of gravity will remain 9.8, and let's choose the masses of the pendulum. Can be anywhere between 0.1 and 1.5. So let's see, we can choose 1.5, 1 half, let's see, 1.5, 0.75, half, and 0.25. Let's do like that. 1.5 kilograms. Okay. 1.5 kilograms. 0.75 kilograms. 0.5 and 0.25. Spanning a very wide range of masses. The length, I'm going to choose 1 meter. And let's see what's the period for this pendulum. Okay, I want to go 1 meter long, 30 degrees. I will reset my timer. Let's see if there's anything else missing here. Nope. Right, I gotta start my timer, and let's see if what's the period of this pendulum for different masses. We start with 1 kilogram. Let's wait for the full swing. Okay, here we go. Stop. I'm getting 2 seconds. Okay? Exactly 2 seconds, huh? 1.5. 2.00. Now we're going to change the mass of the pendulum. 0.75. Here you go. According to the formula, we shouldn't have much deviation from the period. We should get almost the same, okay? But we have to do the experiment to ensure that this is actually what happens in real life. The formula is just a prediction, a theoretical prediction, not necessarily real life. Real life is the experiment that you are doing. So here you go. The timer is started. Let's start the simulation. Go. Let's pause when it gets in there. Here you go. Pause. 206. Didn't change much, right? It's half of the length, the initial length, and didn't change much. Let's take a look here. Now we're going to cut down to 0.5, mass 0.5. Use those lengths that I'm using here. Let's make let's get everybody to use the same values, and we can start. Here we go. Half swing, and when it completes, don't look at the timer, look at the pendulum. Here you go. What I got 204, also very close by. Here you go, and finally 0.25. Okay, reset the timer, start the timer. Start the pendulum. Let's wait for the full swing. Pause. 203. Okay, 203. So our second table is done. You can see that there is not much of a variation in the period. There is a very small variation. We are talking about 6 units out of 200. 6 units out of 200 is 3% variation only. At most 3% variation. This is 3%, 2%, this is 1.5% variation. Anything below 5% is negligible. Okay, and that's my second. Oh, and going back to the equation. See, this equation doesn't have any dependence on the mass. They have dependence only on the length or the acceleration of gravity. Next. Now we're going to adjust the gravity. Repeat the same table here. Okay, put it right in here. We're going to keep the lengths, maintain the mass constant as well. This time I want to put 0.25 for the mass. A very small mass. The length we're going to keep 1 meter. And the period we are going to measure. And I'm going to vary the acceleration of gravity. Let's see what acceleration of gravity that we have available. Let's see here. We have all those accelerations of gravity: Moon, Earth, Jupiter, Planet X, Costume. It is at this very moment that I want you to switch to this other simulation. Okay, it's very similar, but here, you know, we can get a measurement of the actual acceleration of gravity. In the previous experiment, we cannot know the exact value. So let's go ahead and switch to this other simulation. Ruler and stopwatch, we are going to need that. We are going to start with the Earth, just like we did before. Displace 30 degrees. Oh, don't forget to pause, right? Let's pause the simulation first. We're going to start our timer. Okay. In reality, this measurement we already have from the previous experiment, right? But let's do that again. It's going to be 9.8, the first one. Let's see the other ones. Let's write down. For the Earth, what about the Moon? The Moon is 1.62, the acceleration of gravity. Here you go. If you perform this experiment on the Moon, the acceleration should be 1.63. In Jupiter, 24.79. The acceleration of gravity in Jupiter is that large because Jupiter has a very large mass. And which other? Let's put planet X. Okay, planet X is going to be an acceleration of gravity. It doesn't display it. Let's see here.